Hi, my name is Ki Sungbin and my metric number is 195901. Good day to all my examiner and my supervisor. And today I'm going to present my FYP title, which is Design of a Lift System for a Hovercraft. Okay, this is the content. The content is including the introduction, problem statement, aim and objective, literature review, methodology, result and conclusion. Okay, for the introduction, WIG, or also known as wing in-ground effect, is a new type of marine craft. This friction on hovercraft is lower than on a ground and ship vehicle. It can be manual in all terrain such as snow, sea, land, and etc. Hovercraft must sit on a cushion of pressurized air in order to hover. Pressurized air need to be just nice, not too high or too low. Lift fan, a multi-bladed fan, is commonly used to generate air under hull. To propel the hovercraft, engine will be used and electric motor used to generate lift fan. We choose this combination of hybrid engine is because we want it to be light and we can save a lot of the weight on the hovercraft. So the pressurized air is not too high because we don't want the hovercraft to scoop up the dust or any water from underneath of the hull. Okay, problem statement. Hovercraft, hull, skirt and ducting system are the most essential component in the hovercraft. Incorrect entrance air flow ducting design pressure inside the back skirt may not distribute evenly and flip back skirt will happen. Skirt design is important too to make sure no flip-back skirt happen. Aim and objective of this project is designing all components directly related with lift and hence craft mobility. The hull, skirt, ducting system are the most important component. For our objective is to calculate the flow rate of the hovercraft over various operation terrain. To design the hovercraft, hull, air duct and skirt by using SolidWorks, we have to draw it, and to perform CFD analysis by using ANSYS to obtain cushion pressure and the ability of the air duct on the hull to perfectly circulate air throughout the whole hovercraft body may also be tested. Okay, literature review. The craft leaf air escape around the edges of the skirt when the pressure equals the weight of the object. Hovercraft need a steady supply of air to lift it and mitigate for the loss. Hovercraft must be open to more. There's always some leakage, but the designer utilized various strategies to limit the leakage to a low so that just the smallest amount of power is necessary to maintain the air supply. A single engine and motor is being chosen because it was less expensive, had lower noise level and weighed less. Lift and thruster, providing air continuously until the planar chamber air pressure reaches above the outside pressure. Air escape naturally via the opening beneath the skirt, causing hovercraft to rise. The thrust power generated by an engine in kilowatt or horsepower can be used to determine the thruster effectiveness. Four-cycle thrust engine that would only be powered at 85% during operation to prolong the engine lifetime. Duct and fan. Fan and duct that channel a stream of pressurized air. The Performance of duct fan assembly is follow the lift calculator to get the best diameter of duct to provide enough air to the skirt. Okay, for the methodology, study on working principle of hovercraft component and design of hovercraft. Solid work being used to draw hovercraft and its part including skirt. 3D drawing will generate the ANSYS fluent to get result. 3D airflow and pressure will then be analyzed like how the actual hovercraft skirt works. Okay, this is my project flowchart. You can see here we have to study and gain the information first, then we draw if specified, then we can transfer the SolidWorks 3D diagram into the ANSYS, and we will generate to get the air flow and pressure inside the CFD analysis, which is ANSYS. If specified, then we can proceed with the result. Okay, result we have to compare. I done in 3, which is basic analysis of lifting. Required lift pressure, I got 885.55 PA. Hovercraft lift calculator, this is done in the website, which is I got 875.56 Pascal, and this is done in the ANSYS, which is CFD analysis, and get 875 PA. So the required lift pressure for all 3 of this almost the same, so we can verify it. Pressure point parameter value, this is for the rear skirting point parameter value. If you can see here at the back of the hovercraft, the one in the blue color, I just pick randomly and I'll get the result is like 100 102 240 Pascal, which is every point just pick randomly, and the average pressure for the rear skirting is 102 240 Pascal. And next is right skirting point and left skirting point, which is here at the blue color here. The average of the pressure is, as you can see here, this one for the right and this one for the left skirting pressure, which is I just pick randomly to prove that the pressure is distributed evenly in the both side of the skirt and the rear part of the skirt as well. Okay, this average pressure is, we have to minus with pressure ATM here, so we get the required pressure is 875 PA, as you can see here. This one is the average rear skirt, average of left skirt, average of right skirt pressure, and the required pressure, which is show for the whole hovercraft, is 100 102 200 PA for the overall pressure that is happen in the skirt, and minus PATM, then we get the required pressure 870 PA. And here the lower table is from the basic weight calculation, leaf calculator result, CFD analysis result, which is I have explained earlier, and the comparison. We have to compare these three results, which mean that the actual size of the hovercraft can be hover and lift because it have enough pressure to lift up. Okay, next is mass flow rate. Mass flow rate, and we get the cushion air pressure. This is from the lift calculator, and we get it 0.1269 pound per inch square. And we have to refer to the table given, which is here around 0.125, and I did it interpolation to get the air velocity, which is in feet per second. Okay, the air velocity, after we done our interpolation, I got it in 123 feet second. Then the air velocity, I have changed it. I have converted it to mass per second, then I get 37.49. And the calculation of inlet mass flow rate, which is m dot equal to rho VA. Rho is the density of the air, and V is the air velocity, which is we already got here 37.49, and time with the area of the craft, and we'll get around 39.205 kilo per second of the flow rate. Okay, flow rate analysis. Lift air volume. Lift air volume, we have this table, which is I got it from the book, and the operating point value of HFK is given, K is given, normalized drag force is given as well, and we will have to calculate the Q. The Q is the lift air volume, which is in m cube per second. This is what we got for the Q, and the formula is given as well. Then I compare with the lift calculator from the website, which is I got 4.9, and my own calculation, which is 5.63, and this is acceptable because the difference of the value for both lift calculator and my calculation is around 13.95%, and the lift just now, the formula is Q lift equal to CD times AEGH times 2 rho C over rho A. This is the graph. Okay, for the 5.63 only for ground, the ground. Okay, next is to demonstrate using ANSYS analysis result that the hovercraft has the proper design and can generate adequate pressure to hover. The force produced from hovercraft act against the weight so that the hovercraft can be hover. Height pressure ratio is very important for hovercraft to create lift and air cushion. Dimensions such as width and length, weight of the hovercraft, and air gap are inserted into the calculator. Then we will get the value for cushion pressure, air velocity, lift horsepower from the lift calculator. Lift pressure can get by taking weight of hovercraft divided by total hull area. To get air velocity, we need to refer to graph, which is this graph in figure 4.4 from the cushion air pressure value. Okay, for this one is ANSYS software is used to generate CFD analysis when the air is trapped inside the skirting and under the hull region. It will generate an air cushion. The pressure inside the skirt is 102-200 PA. The pressure throughout the whole skirt is nearly equal pressure, which is 102-200 PA. Pressure is low at inlet and outlet because it is open area. The air flow starts from inlet, which propelled by the lift fan, and ends at the outlet, which is known as air gap between skirt and surface of the ground. Okay, for the conclusion is lifting depends on the air velocity, air pressure, air mass flow rate, skirting design, and nozzle plate, and any changes it will have an impact on the outcome. CFD study show that pressure distribution inside the skirting are almost same on the left, right, and rear side. All parts of skirt need to be same pressure to prevent incident of flip skirt when traveling. The result of the weight basis calculation, lift calculator, and CFD analysis are all almost equal for required lift pressure. Okay, that's all from me. Thank you.